Hello out there, high water viewers, and thank you for joining us for today's discussion. It's great to be back after a few weeks off to continue our FE preparation discussion. This week we're focused on pumps. Not the ones you can get for 40% off at Foot Locker, but the big industrial beasts that are the heartbeat of our civilization. And yeah, I know that pumps can be kind of boring, but almost everything we take for granted has some dependence on fluid distribution, whether it's the fuel we use to get to work and distribute our goods, the water and sanitation that keeps us safe, or even the fresh air that we breathe while we're sitting inside an office, possibly recording videos, staring out the window, wishing we were outside getting fresh air. These all depend on some engineer sizing the correct pump for a system's needs. So let's take a look at a few examples that might come up on the FE. One is a typical find a minimum size pump question, and the other involves finding the intersection between a representative pump curve and the required system curve. So let's head over to the blackboard and get started. Alright, so let's get started on our first example here. What we have is a system where we want to size a pump, and what we need to do is find what's the minimum required head that this pump needs to provide. For this system, we want to supply 8 cubic feet per second along 2,000 linear foot of 10-inch pipe. We have a static head of 30 feet, and the friction coefficient is 120. Now, hopefully, when you see this problem, you're going to start thinking immediately of what kind of equations you're going to need to use to solve this problem. I won't give it away yet because I want to give people the opportunity to pause the video and give this example a shot on your own. And if you really want to study the best way possible, I would recommend using the FE review PDF that's supplied, because that's what you're going to use on the exam. And then give it a shot, come back in a few minutes, and then we'll walk through the solution. Okay, welcome back. I hope that went okay for you. So when you see when you see friction coefficient, you know you're probably looking at some kind of relationship between velocity and friction, right? And when you're talking about pipes, you're going to be talking about the Hazen-Williams equation, pretty much all the time. So that's going to be the easiest, most straightforward way of developing a relationship between fluid velocity, pipe material, and your head loss per linear foot. Static head is basically whether you have, even when you have zero velocity, you still have some amount of head that needs to be overcome. This could be like elevation change, or usually it's probably going to be elevation change. Everything else is going to be a function of velocity. So let's walk through the solution here. So we have the Hazen-Williams equation where velocity is going to be equal to, let's start with C. C is going to be your coefficient of friction. This is something you're going to look up in a table. I'm pretty sure it's supplied in the FE review, or not review, but the reference handbook. They're going to have tables. Usually the tables have some kind of a range of values. The range of values could be different between different types of materials or different manufacturers, but more often than not, it has to do with how old the material is. So if they say old pipe, it's going to be on the higher end of that range. If they say new pipe, it's going to be the lower end because it's newer, it's less friction. But if they don't give you any information to go on, just pick a value in the middle and you should be fine. That's generally what you're going to do. Okay, so you have your coefficient of friction. You have, and this is going to be based on the material, right? So it's going to be like smooth concrete, or it's going to be iron pipe, or whatever. That's how you're going to look that up. Then you have your hydraulic radius. We've talked about this before in some previous videos. Hydraulic radius basically has to do with the relationship between the wetted perimeter and the geometry of the pipe, or the material that's conveying the fluid. It doesn't necessarily have to be pipe. But in this case, since it is pipe and we're talking about pressurized pipe, it's going to be a pipe flowing full, which is definitely the easiest type of hydraulic radius to solve. And then we have the hydraulic slope. Now this is probably the thing that's going to catch people up the most often. This is not slope as in, change in elevation per length, right? That's typically what we think of as slope, and we usually think S as slope. This is, however, the hydraulic slope, which has to do with the change of gradient, the fluid's energy gradient per linear foot. So this is where you're going to lose energy because of friction. So in other words, it's basically frictional loss per linear foot. Is not always exactly right, but that's generally what it is. So what we want to do in this case is solve for our hydraulic slope. That way we can add this back into our static head, and then for 2,000 foot we can get what do we need for this velocity for 2,000 foot of pipe, add it to our static head, and then we know our total energy that needs to be supplied by a pump. Okay, so let's get this started. So our hydraulic slope, if we rearrange this equation, it's going to be velocity. Oh, and I totally forgot to our K value, because this is an empirical equation, our K value it's a correction factor for the units that we're using. So if you're using American units or whatever they're called, then you're going to have this correctional factor of 1.318. And if you're using units anywhere else in the world, you're going to have 0.849. All right, and so that just basically lines the linear relationship up with the data, with the observations. So, okay, we have our K value, we have our coefficient of friction, we have our hydraulic radius, and oops, what am I doing here? Sorry. And then we want to, correct for the exponent on the hydraulic slope. So one thing we need to do is solve for velocity, right? Because we're not explicitly given the velocity, but we are given the volumetric flow rate. And so this is something that hopefully you're going to be able to just know off the top of your head. There's probably the equation in the reference material, but the continuity equation is something that's going to come up so often that really if there's one equation you should know off the top of your head, this is going to be it. Where the volumetric flow rate is, of course, this is going to be volume per time. Well, if you divide your area of your pipe out of that volume, then you have a velocity. That's basically any particular molecule of water is going to be moving at this velocity. If you have an area of those, then per time it creates a volume. So in this case we have 8 cubic feet per second, and our area is a 10-inch pipe, converted into inches, and then we find the area is going to be 14 feet per second and some change. Okay, now once we have this, we can substitute this back in for velocity in our equation, and we can solve for our hydraulic slope. Using the correction factor for American units, our coefficient of friction, which was given to us in this case, we didn't look it up, and then our hydraulic slope, is going to be, since we know we're working with a pipe flowing full, in this case it's going to be the diameter in inches over 4. And that's just, if you were to do the math and solve it, that's going to be what you have for a pipe flowing full. But again, since that is so typically used, that's another value that's worth just knowing off the top of your head. Look up hydraulic radius for pipe flowing full and just kind of have that one under your hat ready to go. Okay, so if we crunch those numbers, what we have is 0.088, and that is going to be our head loss per foot of pipe. Okay, so let's get another page here. And so what we need, our total frictional head loss is going to be our hydraulic slope times our distance for our frictional loss. And so in this case, we've pretty much got this solved. So we have 0.088 times 2,000 foot is 176.64 feet. And then our total head that is required is going to be our frictional loss plus our static head. So in this case, this is pretty obvious at this point. We have 176 plus our 30 that was given to us in the problem statement. It's going to be 206 and some change feet of total head. So any pipe that we select for this system is going to need to be able to provide at least that much head. All right, well, I hope that went well for you. Let's move on to the next one. Okay, let's take a look at our second example. In this example, we have we want to solve for the flow rate for some kind of pump. Now, in this case, we're given a particular pump, and we're given a particular system that we're applying the pump to, and we want to solve the flow rate that we would achieve for this particular pump and system. This is probably a little bit less intuitive of a question. If you don't already know how to do this, it would be one of those that's probably going to be a little difficult to figure out, on the fly. So this is definitely one that I suspect will come up, certainly could, and it's one that's worth understanding because it's really easy if you know how to do it. It's just again, it's like something that's a little bit hard to figure out if you're not familiar with it. So what we have here is a pump curve. This would be supplied by your manufacturer when you're looking at a pump or you bought a pump or whatever. It's going to have a pump curve, and the pump curve relates the head provided to the flow rate. So for any particular flow rate, it's going to provide a certain amount of pressure. On your system, you're going to have, again, a static pressure that needs to be supplied and some kind of frictional loss based on flow rate, because of course flow rate for a pipe is going to have a particular velocity, and the higher the velocity, the more frictional loss you have. So those two together are going to give you your system curve. So that's all the information you need in this case. So if you want to pause the video, try to solve this one, come back in a few minutes and we'll go through the solution. Alright, well, I hope that went well for you. Let's take a look at the solution. So the first thing we need to do is develop the relationship between our system that's going to require head and the pump that's going to provide head. So basically our pump is going to be equal to our system. And we want to find the intersection. Okay, so we know our pump curve, right? That was given to us by a manufacturer. Our system curve is simply our static and frictional losses. So if we put this all together, we have our pump curve equal to our system curve. Right? And we basically just want to solve for Q. So let's start a new page here. So let's just kind of, I mean, you guys know how to do algebra. So let's just kind of go to the end here. All right, we get this in terms of Q, and then we have our flow rate. Okay. I actually have not done the numbers on that. Let me put that in the calculator real quick and come back. Okay, I'm back with the solution and actually realized a couple of things. One is, if you haven't already, I would definitely recommend checking what kind of calculators are allowed to be used for the FE, and make sure that really, I would recommend getting one now and becoming familiar with it. You know, use that one while you study for the FE, because you don't want to be trying to figure out how to use it while you're taking the exam, obviously. The other is that it's really important to kind of have a feel for what a correct answer looks like or feels like, right? Because I crunched the number on this and immediately was like, nah, that don't look right. And I realized I forgot to take my square root. So, just being able to kind of have an idea of what the answer should look like, within a range. That way, if it's not that, go back and check again, like I did, and realize, yep, I made a mistake. So once you've taken the square root, you will have the solution of Q equal to 124 volumetric units based on what the volume of Q was. So some typical units would be like gallons per minute. And so there you go. It's pretty simple if you know how to set these systems up and find the intersection between the two curves. So that is going to wrap it up for pumps on this discussion. We'd quickly like to thank everyone who has supported the channel, watching our videos, leaving comments, likes, subscriptions, all that stuff. Super great. Obviously, something that really helps us out. And good luck on your FE.